Okay, so the plan is to review the 3 chapters that are going to be on the exam, which is chapters 21, 22, and 23. And guys can already see I'm having some issues here with my mouse. Maybe I can type it. So it's going to be chapters 21, 22, and 23. Right, what's going to be on those chapters? Well, chapter 21, this is the one on electric force and electric fields. Okay, so this is like Coulomb's law. Coulomb's law. Electric fields, obviously. And I think there's a little bit of stuff about conductors and insulators in this chapter as well. Okay. How about chapter 22? Chapter 22, this was the chapter on Gauss's law, so it's like all about Gauss's law here. But there's a kind of some preliminary stuff, right? Electric flux was kind of like a preliminary topic for us. And so we kind of talked about electric flux and then did Gauss's law, and then we kind of just did Gauss's law from there. So yeah, it's really just those 2 topics there for chapter 22. And then chapter 23, which is our latest chapter. This is electric potential energy. Well, the chapter is called electric potential, so let's put it there. And we cover electric potential energy. We cover electric potential, and usually we put the word difference here. And actually, now that I think about it, we talk about electrical work first. Okay, and that's it. Yeah, those are basically like the 3 main topics in chapter 23. Again, in all 3 of these chapters, this idea of conductors and insulators is present. Okay, so this idea of conductors and insulators really falls under chapter 22 and chapter 23, right? We're always kind of looking at conductors and insulators. So for example, in Gauss's law, like when a problem says you have a uniform charge density for a sphere, if the volume of the sphere is charged, right, then you're talking about an insulator, right? Because for a conductor, the charge always moves to the surface, right? And the reason for that is because its charge can easily move through a conductor. So there's stuff about conductors and insulators in all 3 of these chapters. So pay attention to that stuff. That will be relevant on the exam. Okay. All right. So that's the outline there. So let's go ahead and get started with stuff. And again, this is going to be like Cliff Notes type of stuff. We're going to like kind of review. We're not going to go into so much detail, like deriving everything, because we do want to have some time for some examples. Okay, so I'm going to delete this. Start things off with chapter 21. Oh, okay, my mouse seems to be working now. So this is the chapter. Let's go ahead and just get right into it. So Coulomb's law. Where does Coulomb's law come from? Where does Coulomb's law come from? Where does it come from? Well, it comes from the fact that Newton already figured out his law of gravity. That's really where it comes from. So Coulomb postulated a force which was proportional to the product of 2 charges. The proportionality constant is now called Coulomb's constant. Proportional to the product of the 2 charges here. I hope my mouse doesn't keep giving me this much trouble here. Like so. And also proportional to 1 over the distance between the 2 charges squared. Okay, so Coulomb's law is like a postulated force law. And what you do is you kind of guess a law like this, like Newton guessed his law of gravity and then was able to show, yeah, this definitely works. When he checked if he could calculate the orbits of Mars and Venus and Jupiter. Okay. So he guessed a law. He knew it had to have a certain form. And then when he guessed it, then he checked it. He went through and calculated the orbits of the planets and then compared that to astronomical data that was available at that time. For example, due to Johannes Kepler. And then when he looks at it, he says, wow, this agrees with my theory very well. And so then Newton's law of gravity is now an accepted law. Same thing with Coulomb's law. So Coulomb knows it has to be the product of the two charges in the numerator, kind of like the product of the two masses for Newton. And he knows it's got to be 1 over the distance squared, because the force is spherically symmetric. No matter where I put the other charge, it still experiences the same force, no matter where that charge is on a fixed on the shell of a sphere, basically. Okay. And so this law is then tested against experiment. And then we see, okay, yeah, this is working, or, oh, wait, this is not working. And it turns out it's working. Okay. And so this is a force that is literally just, here's a guess. What does experiment say? Okay. Experiment says it's working really well. Okay. And, Coulomb probably guessed maybe some other types of forces or something, and then finally stumbled upon this one. But actually, if he just followed Isaac Newton, then he just said, okay, this is the force, and now test it, it works. Okay, so what do we do for problems like this? What are the meaning of these terms? Well, we have a charge Q1, and we have a charge, let's say negative. We have a Q2 here. Hopefully my mouse is not giving me too much trouble here in a little bit. It's very finicky sometimes. Okay, so we have a Q1 and a Q2, and the distance between these two charges here is R. This is what we mean by these symbols here, Q1, Q2, and R. All right, so what are some types of problems we might come across with Coulomb's law? Okay, one example of a problem we might come across is if we were to say, okay, this charge here is 4 times as big as this charge. Oh, what am I? No, I meant to write Q here. This charge on the left is 4 times as big as this charge on the right. And we might ask, okay, where in the center here is the force going to be equal to 0? So we might say F equals 0. Somewhere in the middle here, where is that point where F equals 0? How would we tackle this problem here? Okay, well, whenever we're talking about force, we have to introduce this idea of a test charge, right? A Q0. And the test charge is going to be somewhere right here, and it's going to experience 0 force. So what do? Well, we say the force due to charge 4Q has to be equal to the force due to charge minus Q. Okay, a test charge is always positive. So it's going to have a repulsive force. It's going to have a repulsive force due to the 4Q. Okay. And it's going to have an attractive force due to the minus Q. Okay, well, wait a minute. The point that I've labeled here, both forces are to the right. So it's not possible for the force to be equal to 0 in this region. Okay, what about this region? Put a test charge there. I put a test charge here. I say, okay, what's the direction of the force? Well, if this is my Q0, I have a repulsive force in this direction. I have an attractive force in this direction. Okay, it could be 0 here. The net force could be 0 here. But then you say, oh, wait a minute. I'm always closer to this bigger 4Q charge than I am to this smaller minus Q2 charge. Well, that means that this force here is always going to be bigger than the force of attraction here. And so the force cannot be zero here in this region either, which leaves this region. Okay, so now I have a clear picture of what's going on here. I can figure out where that force is going to be zero now. So this is my Q0 now. Let me try and make it look decent. This is my Q0. Now I know, okay, I'm closer to this one, so this force can be this big. The repulsive force can be this big. They can match. Somewhere in this region here, they're going to match. Okay, and so how do you set this up? Well, the force between the 4Q charge and the little Q0 is K times 4Q over, with a Q0, my bad, with a Q0 here, over R squared. But what's R? Well, this R right here is this distance here, from here all the way over to here, right? Let me go ahead and clean this up a little bit. Let me see if I can pull this over here. Get rid of this check mark. This is super messy, I know. Bear with me here. This distance here, wow, that's a nice straight line there. Hopefully my mouse is working again. That's the distance R there when I write it here. Okay, that's the distance R there when I write it there. This is an R. Okay, and then here we have another R, don't we? We have another R. Okay, let's call this one X. Let's call this one X here. Please work. There we go. Okay, we have an X, we have an R, and we have an X. Okay, so just setting this up simply now. We have a 4 times KQ over K0 over R squared. For the left side, on the right side, what do we have? Well, we have a minus Q, but we've already set the two forces equal to each other, so we don't need a minus sign. For this particular one, it's minus capital Q, so it's just capital Q, so K, capital Q, and then we have times Q0, because it's an attractive force between the minus Q and the Q0, divided by, and now not R squared, but X squared, okay? X squared, okay, my mouse again, X squared there. Okay, so what do? Well, notice Q0s always cancel here. Whenever you're looking for when the force is zero, the Q0s always cancel. Why? Because there's always going to be a Q0 on both sides of this equation here. We have two forces, one minus the other equals 0. We move the negative one over to the other side. We cancel the Q0s on both sides. And now the last thing we need to do is figure out the relationship between R squared and X squared. Okay, what's the relationship between R squared and X squared? Well, we have to label the distance between the two charges. Grab another color here. So the distance between the two charges, if it's fixed, if we call it D, right, which is often what you're given in a problem. Usually D is going to be something like, I don't know, 4 centimeters to give an example. And so what we do is we look at what is R in terms of D and X. R is equal to, well, R is this full big distance here. Well, R is going to be D plus X, right? R is going to be D plus X. When we plug that in here, we can't forget to square both the D and the X here. We got to FOIL it out, right? So it's quantity D plus X squared. All right, so that's how we set up a problem like that. Let me see if I can clean this up. I'm going to clear this and I'll rewrite the setup here, okay? Give me a thumbs up if that's okay. I'm going to clear this because it's kind of messy, and then I'll try and write it nice and neat. Give me a thumbs up if you're good with that. If you have a question, let me know you have a question. Okay, doesn't look like we have a question. So let me rewrite that for you guys. So let's hope for Q. Okay. Actually for K, Q, little Q0 over. Oh wait, we already canceled the Q0s. We already canceled the Q0s. Okay. Divided by now X, or rather I said d first. So d plus x squared is equal to, and k, q, notice the k's also cancel here. The k's also cancel. Q, we canceled q zeros already, so just q, over x squared. Okay, so look at this. Look at this. Everything is canceling. We have so many constants in our problem here. A lot of those constants are canceling. And so what we have is a nice, neat expression here. 4q over d plus x squared equals q over x squared. What do we do to solve this? Like, let's say we're solving for x here. My recommendation for solving for x is to multiply these denominators to the other side. So 4q, oh nice, my mouse is working again, equals q times d plus x quantity squared. Multiply the terms over like so, and then take a square root right now. Take a square root on both sides right now, okay? And don't forget to put a plus or minus on one side. So let's put the plus or minus on this side. As long as we have plus or minus on one side, we're good, okay? So put your plus or minus, put your plus or minus there. Actually, now that I'm thinking about it, I think I made a mistake earlier. If we have a plus and a minus here, we can have a 0 over here on this side when we're closer to the minus q. I said we couldn't have a force equals 0 here. Yes, we can. We can have a force equal to 0 here at this point, which is closer to the negative charge than it is to the positive charge. So maybe you want to fix that in your diagrams, okay? We can have a force equal to 0 when we're close to the negative charge on the inside here, when this one is 4q and this one is minus q. Okay, so two answers here. So an answer here, and we'll also have an answer over here. So we'll have an x and we'll have a negative x. And so that's why the plus or minus makes sense here. The plus or minus makes sense because we have two answers. One for when we're out here, this direction, and one for when we're inside this direction. Okay, does that make sense? Give me a thumbs up if that makes sense. We don't have numbers, so we're not going to solve it further than this. But when you have a plus or minus, make sure you choose the plus sign, solve for x, then choose the minus sign, solve for x. You got your two answers.
Professor, so wouldn't that not make any sense? Because if the test charge is being repelled by the positive and attracted by the negative, then that one in the middle wouldn't cancel out.
Yeah, it can happen. It can happen. You're right. It can happen. So this one is repulsive, but if it's far enough away, then it can balance this one here. So to your point, actually, it's very important. There are values for D which there is no solution in this region. That is true. But it depends on the value of D. If the two charges are too close together, then you may not necessarily be able to do it. So it depends on the Q's, and it depends on the value D. Does that make sense?
Okay, sounds good.
So yeah, so it does sort of have to be the perfect combination for you to have an answer. Okay, so any more questions about that, or should we move on now to maybe electric fields? Okay, quick comment before we move on to electric fields. Look at these expressions here. Look at these expressions. On the left side, we have Q over R squared. On the right side, we have Q over R squared. This is basically the same exact problem as the following. Where is the electric field equal to 0? Does that make sense? If I ask the question, where is the electric field equal to 0, you apply this exact same analysis. Okay, so wherever the force equals 0, that's where the electric field is going to be 0, right? Because if I put a test charge in a spot where there's 0 electric field, well, there's not going to be any force. So that's the first comment there on electric fields. Let's go ahead and write it out here. So electric fields, we usually use E with an arrow for electric fields. So E fields here. What do we know about E fields? Well, we know that the electric field of a point charge, if I have a point charge here, we know that the force on test charges Q zeros that we put near a bigger positive charge labeled, let's say, plus big Q here. If I were to put a test charge here, a little plus Q0, there we go, Q0, then the force would be radially outward. So we could imagine dragging this little test charge all around this big positive charge plus Q and mapping out these force vectors, okay? We map out all these force vectors, and then what we do is we divide those force vectors by the test charge little q, okay? And when we do that, we get rid of that Q0 in our force expression, and we're left with an electric field for a point charge of KQ over R squared. Electric field of a point charge KQ over R squared, and it has a radial direction. It's positive R hat for a test charge, for a positive charge, and it's minus KQ over R squared R hat for a negative charge. So the vectors are pointing inward towards the charge. So for a minus charge over here, the electric field vector is coming in radially like so. Okay? Out for plus, in for minus. All right, so that's just for a point charge, but obviously we've dealt with problems with electric fields of spheres of charge, excuse me, disks of charge, rings of charge, and so forth. So how do we figure out the electric field for some of those kinds of charge configurations, right? Because it can get a lot more complicated. Well, the first thing that we do, I'm assuming everyone's good on point charge. Give me a thumbs up if we're good to move forward. Only a couple people give me a thumbs up. Thumbs up if we're good on point charges here, or if you have a question, just type it out in the chat or ask it with your voice. Okay, that was much better. So we'll go ahead and we're going to clear this. We're still on electric fields, though. We're still talking about electric fields here. The next thing to do is to imagine you don't have point charges anymore, but you have a distribution of charge. So when you have a distribution of charge, you have a small contribution to the electric field, dE, and that dE is and actually let's okay, it's fine for now. It's fine for now. We'll use R hat here for now. We have a small contribution to the electric field at some point P, dE. And the amount of charge which is contributing to that electric field at a point P is dQ. So let's get a picture here. Suppose we have some sort of charge distribution like this, some sort of potato shape, and there's a little volume here of charge, and that volume there has a charge amount of dQ, and we're interested in the electric field at this point P over here, and so dQ is at a distance, let's say this is the vector R here. It's at a distance R away from that point. And so the electric field, let's use another color here for the electric field. The electric field at that point, or the contribution by dQ to the electric field, is dE. Okay, and so that's the philosophy here. I see there's a chat. Okay, got it. Okay. So that's the philosophy here. And then what do? Well, we then vary dQ. So we look at dQ now as a volume over here. So we integrate over all of this density. We move this dQ and we sum all of the parts. So now our R vector is over here. We'll call this one, call this something else, maybe R prime or something. Okay. Well, actually, no, this is the same R vector here, only the coordinates, the three-dimensional coordinates here of these guys change, but this is the same vector R here. Or rather, oh, no. Okay, so let's actually be more precise about the labeling here. So we should, if we're going to have an origin like this, the vector R this is not the vector r, but let's try to be precise here. We'll use the vector r from the origin to the point. Okay, and then we'll use the vector, this vector here is some other r. We'll call this one maybe a vector, call this one a capital R. Capital R only ranges inside the volume here, and then maybe this vector right here, we can call this vector, we'll call this one like, let's call it x. Okay, let's call it x. All right, so just to be really precise there. So since, yeah, I know it could be a little bit confusing here. So in that case, actually, you know what? No, switch the labeling here. So make this vector r, so that way this stuff over here stays the same, and then we make this vector x. Make this vector x. This is the vector x. Okay, and so for a three-dimensional picture, it can get a little bit complicated. So how do we simplify this down? So we've got these dq little volume elements which have an amount of charge dq, and the distance from that element dq to the point P we label r. And there's some other vectors here in the space that we can get rid of if we have some symmetry in our problem. And so that's the next thing to do. Okay, so that's the next thing to do. So what we do now is we take a look at certain examples. Like, for example, we have a sphere, and we center the sphere at the origin, like so that this is the origin here. And the sphere has a radius, let's say a. And what we do is we look at the density of this sphere, rho. We take little patches, like so, okay? And how far away this this patch is, this volume element from the center. That's what we called big R here in this other picture here. And then from this volume element over to some point, let's be careful here. So here is the z-axis. We're interested in the point P right here. This is a P, not a rho. Then that vector from that element dq to here is the vector r. Okay. And the vector x is the distance from the origin up to this point here. So x. And now you can kind of see this is like what we've already done, right? So x now is measured. So we could call this actually the x-axis, not the z-axis. So this is our x-axis here. And so now you can see this is starting to get a lot more familiar, right? So a distance x away from the center of a sphere, what's the electric field? Well, we have to integrate over the charge density of the sphere to get the answer. In the case of a sphere, though, the answer comes out nice and simple. And we know it comes out nice and simple just from thinking about Gauss's law. We could do the integral too, though. That it's simply the same as a point charge. And instead of r here, since we're interested in this point, which is a distance x from the center, we'll put x. Okay, so it's kq over x squared. This is the total amount of electric field. And then we need to put the vector sign in there. So let's put x hat. And it turns out that no matter how far away we are from the sphere or in what direction, the electric field is always going to be radially outward. So then we can transform this thing to a kq over r squared with an r hat vector. Okay, let's do an example now. Let's do an example where we actually integrate this thing. Okay, so that way we have like a concrete example to go along with this using dq. By the way, q here is rho times the volume of the sphere. If we have a uniform charge density here for this sphere, rho, and then multiply rho by the total volume of the sphere, we get the total charge of the sphere. And that's going to be kq over r squared r hat. Okay. All right, we'll show what the electric field is inside the sphere when we get to Gauss's law. Okay, so let's go to a concrete example now. So let's take a look at a disk. I don't believe we did the disk in class before, but I think I did give it as an assignment in a homework, but I don't think we did it in class. So we're interested in the electric field at the point P here. So this is going to be the electric field. It's going to point in that direction. Okay. Now this disk will say has a charge density sigma. Sigma because it's a surface. It's not really a volume because it's a disk. So sigma, which is defined as the amount of charge divided by the area of the disk in the simple case where sigma is constant and uniform. Okay, so uniform density. Well, that's nice because that can pull right out of any integration that we have to do. So if we have this charge density here, what we have to do is we have to figure out the components of the electric field which correspond to a certain charge element. So let's get some labelings here. So the radius of the disk will be A. Are we going to have to integrate over A? Yes, we are going to have to integrate over A because this is a disk, not a ring. If this was a ring, we wouldn't have to integrate over A. Okay, are we going to have to integrate over theta? Yeah, you bet. We're going to have to integrate over theta. Why are we going to have to integrate over theta? Because the density of the disk is uniform around theta, right? So if we're going to integrate all of the patches of charge here, we're going to have to integrate over theta, okay? So if we were to draw a little patch, I'll draw a little patch in there in a second, actually. Let's take a look. Maybe down here, we can draw a patch right now. So a patch here for us for an angle d theta would look something like this. This is our patch here. This is our patch of area dA. Area dA. Okay, and what is dA given in terms of? Well, dA is given in terms of the area element of a disk, right? So it's r d theta dr. Okay, so r and d theta usually come as a combo, right? And then we have to integrate over r. Now the problem here is going to be that, okay, we've labeled the radius here as a, because oftentimes in these problems they reserve r for being the distance from where the charge is to the point you're interested in. Okay, so we're going to do the same thing. So normally we're used to seeing the area element as r d theta dr. We're going to change r to a now. So a d theta dA. This is the radius on the disk. Okay, this is the radius on the disk. We're going to reserve r for the distance from the charge to the point P. So this is going to be our r vector here. And actually, let's clean it up a little bit. Let's clean it up a little bit. Let's make it look nicer. Okay, and I'll actually do a straight line like this. Okay, there we go. So there is our r vector. And then this distance here, we're going to call this x. So that's how far away we are from the point P to the disk. How far away are we on the from the center location to the point DQ? Well, we're a distance a, right? We're integrating over a. So actually, we probably should change lowercase a to maybe something like a capital A. Okay, capital A for the radius of the disk there, and we use a to vary the radius. Okay, so slight change there. Sorry about that. So the radius of the disk is measured as A. The maximum radius of the disk we'll call capital A. Actually, why don't we call it capital R? We're not going to have a capital R in this problem, so let's call it capital R. That's even better. So the full radius of the disk is R. The radius measured on the disk is A. So we'll integrate from 0 up to capital R when we integrate over dA. Is that clear? Can we give me a thumbs up if that's clear? So we're going to integrate A from 0 to capital R.
So is that A d theta dA would be big R d theta?
No.
Oh,
No, it stays A. It stays A. A is the variable.
Oh, the variable.
Radius.
Okay.
Yeah. And then we'll integrate that from 0 up to big R. So big R is the constant here. A is the variable. Okay, so now what do? Well, we have to start looking at triangles now. So for any patch of charge here, it's going to be a distance A away from the center of the disk. And it's going to be a distance R away from the point P. And it's going to have, it's going to be a distance. So if this point right here is the center of the disk, the distance from the center of the disk to P is X, right? Okay, so now what? Well, our vector here, E, is going to be in this direction if sigma is positive. Let's assume sigma is positive for simplicity. What is going to be the component along this direction here? Along this direction? Well, it's going to be the cosine of this angle theta, right? Let me use another angle here. It's going to be the cosine of an angle phi, which is here, right? So if this is E, this would be E cosine phi. Let me try to clean it up. Mouse is giving me trouble again here. Actually, let me use the text, maybe save some time here. So this is E cosine phi here, and then this is E. And I'll just state the magnitude here. It's clear what the directions are from the picture, right? It's clear what the direction is from the picture. So we'll leave it like that. What about the sine component though? What about the sine component? Here's the sine component. E sine phi. Well, we already know that the disk is symmetric about its axis. So the E sine phi piece is going to integrate away. We don't need to account for the E sine phi piece because all of those vectors, as we integrate around, if we're to look down the axis of the cylinder, like it's a telescope, what we would see is we'd have all of these electric field lines pointing in all of these directions at the point P. Okay, so this is the point P here. If I can write P there. That's the point P, and these are all the electric field lines which add up at the point P, which are E sine phi. And all these E sine phi's are going to add up to 0 because of the symmetry. Does that make sense? Give me a thumbs up if that makes sense. All these E sine phi components will add up and
Can you
cancel
say that
out.
again?
What'd you say?
Can you repeat what the E sine phi thing again?
It's this component of the vector here, of E. So maybe to elaborate a little bit more. So this is our DQ element right here, right? This is our patch DQ, like this guy in blue over here. This is DQ here. It's the patch in blue. So this DQ element gives rise to an electric field which points in this direction. You see that?
Yeah.
Okay, so that electric field has two components. It has an E cosine phi and an E sine phi, right?
Right.
There's also going to be a patch of charge down here, right? You see that? And so that patch is going to have an electric field which goes in that direction.
Oh, they cancel out.
And they cancel.
Okay.
Exactly.
Okay,
And that's true everywhere on the disk, right? There's going to be one over here, and there's going to be one over here, right, on the disk.
Yeah.
So their components will cancel as well.
Oh, okay, got it.
Make sense? Okay.
Yeah.
So let's try to back all the way up there. Okay. So, oh, there's that one too. Okay. So what do we do then? Well, we can just ignore the sine phi piece because it's going to drop out. So this angle here is also phi, right? From vertical angles theorem from all the way back in your geometry class in high school. Those two angles have to be the same. And so we can figure out that cosine phi is actually given in terms of the triangle. Cosine phi is given in terms of the triangle. What is cosine phi? Adjacent over hypotenuse. So x over r. Does everybody see that? Here's phi. X is adjacent. R is the hypotenuse. So cosine phi is x over r. Okay? X over r. All right, so if we want the total electric field, E, we have to integrate dE. Integrate dE as a vector. Okay, well, what's the direction of the electric field? Well, we just talked about how all the sine phi components are going to cancel. And so we're only going to have an electric field which is in the x direction. So we can account for the direction simply by putting an x hat in the end, right? So we'll put an x hat. We'll just pull the x out all the way out of the integral. We don't actually need to integrate over x. X is fixed in this problem because the disk is always a distance x away from its center to the point P here. This is the point P. So x never changes. No matter where we are on the sphere, x is remaining constant here. So we'll put an x hat here to account for the direction. And then we're going to have to integrate twice. Why do we integrate twice? Well, we have a theta that we have to integrate over, and we have an a that we have to integrate over. Okay, so it's a d theta dA. And what are we integrating over? Well, sorry, this is what we're integrating over. What about the electric field part? Where's the electric field? Well, it's Coulomb's law, K. Oh, excuse me. Let's slow it down a little. I'm trying to go fast so we can kind of touch on more topics, but maybe it's not a great idea. We need to integrate K dq over r squared, and indeed it is indeed we are integrating over r squared here. I know from this picture it doesn't look like r is changing, but remember that r is changing because we have a patch of area here as well, and the r value for there is going to be a different r value. Okay, so r is changing. I see there's a chat. How did you determine the order of integration? We'll get to that in a second. I haven't determined the order of integration yet. So k dq over r squared, that's what we're integrating over. So we're integrating over dq here. It's going to be two integrals because dq is given by sigma times dA. Okay, sigma times dA. Right, just looking from our definition over here. It turns out, though, that sigma is constant, and so sigma is really just the total charge divided by the total area. But since we're integrating over sigma, we better put sigma dA for dq, okay? Now let's replace dq with sigma dA. So we have the direction here is x hat. We have two integrals. We'll talk about the order of integration in a second. Coulomb's constant pulls out. Let's pull Coulomb's constant out. Does r squared pull out? No, r squared does not pull out because it has a. A is in the r term. R is going to be square root of a squared plus x squared, right? So that's r is a variable here. So sigma dA over r squared. So x hat, Coulomb's constant here, two integrations, and now we replace we replace dA with a d theta dA, like so. Still divided by r squared here, it doesn't change. Now we can talk about order of integration. Nothing in this problem depends on theta, so we might as well integrate over theta first. Doesn't matter if you integrate over a or theta first, because this integral is convergent. We were essentially integrating a constant over this distance r, which varies as square root of a squared plus x squared. It's going to be squared in the denominator, so we're essentially integrating over something like 1 over a squared. Okay. And so that piece, we can do that piece first if we want to, but that piece doesn't depend on theta. And so it doesn't matter which order we do the integration. We can integrate over a, and we can integrate over theta. Okay. So does that answer your questions, Sergio? So the theta and the integration over a will not depend on each other. So it doesn't matter if we go one or the other first. Okay. All right. So carrying on the side now, or maybe I can get some space here like so. Get some space here like so. We can, we can move. Oh, and by the way, I've already forgotten here. I've already forgotten to put cosine theta. I've already forgotten to put cosine theta here. How come nobody said anything? Okay, so let's put cosine theta in here. Remember, we're integrating over e cosine, or sorry, not even theta, phi, e cosine phi. So cosine phi needs to be in here. Cosine phi needs to be in here. Where does the cosine phi come again? Let me just remind you. Each of these components of the electric field from dq are making an angle phi with respect to the x-axis. So the cosine phi component is the component that will be non-zero after we integrate. The e sine phi component will be 0 after we integrate, because we're integrating around a full circle. So again, there's cancellation. There's a dq down here, which has an e sine phi term, which will be pointing up, and it will cancel that e sine phi term, which is pointing down. Okay, so we need the cosine phi in here, since we're looking at just this x component here, which is the only non-zero component. All right, back to the integration here. Cosine phi, we've got to replace cosine phi. Cosine phi is x over r. So x hat k double integral. Let's just do the integral limits now. So 0 to 2 pi for 0 to 2 pi for the what is the thing we're using here? Theta, for the theta integration. Okay, and then what are we going to integrate for a? Well, we have to go 0 to big R. Oh, sorry, 0 to big R. 0 to big R. Okay. All right, now some of you might be worried, wait a minute, 0. Hold on a second, we're basically integrating something like 1 over r squared. So how are we going to deal with 0 here? But we're not quite integrating 1 over r squared. Remember that, okay, we have sigma here too. Let's pull sigma out of the integration as well. Remember that r depends on a and x here, and a is what we're integrating over. So there's this constant piece, there's this constant x piece here that prevents us from dividing by 0. Okay, let's pull out the sigma. There we go. So we have, now we have, oh, and also the x from the cosine phi is also constant. So a d theta dA r squared. And we have cosine phi. Let's replace cosine phi now. Cosine phi is x over r. There it is. The x is also constant. The x is also constant. Look at x here. X is fixed. It's the distance between the center of the disk to the point P. Okay, so we have some constants here. We have x hat, we have k, we have sigma. We can pull out an x. What else can we pull out? We can't pull out anything else. A is a variable, theta is a variable, A is a variable. R has an A in it, so it's a variable. All right, double integral, 0 to R, 0 to 2 pi, A d theta dA over R cubed. What is R cubed? It's A squared plus X squared to the 3/2 power here. The 3/2 power here. Okay. And I'm not going to ask you to do any kind of crazy integration like this on a test where you actually have to go through and like figure out, oh, do I use a U sub? Do I do a trig sub here? What do I do? No. So what we'll do is we'll just look this integral up using a table here in a second, or we'll punch it into Wolfram alpha and it'll spit out the answer for us. But it isn't that bad of an integral. You should know how to do it. Notice that's what's in the parentheses here is a squared plus some constant. So I can set u equal to this stuff. I can set u equals to a squared plus x squared because I have an a up here in the numerator. So du is going to be equal to 2a dA. So look, we have an a and we have a dA there. So this integral is not difficult to do. It's basically 1 over u to the 3/2. That's going to integrate to, what is it? It's going to integrate to u to the minus 1/2. So the answer that we're looking at here by the end of everything is something which is proportional to like the square root of a squared plus x squared. Something like this. It's going to be proportional to a term like this. Excuse me, actually the a squared will be replaced with an r. It'll end up being r squared plus x squared, something like that, okay? Because we're going to plug in r. So that's the idea there. That's how you set these problems up. Let's go ahead and look up the integral in a table now. So you guys go through the u substitution on your studies on your own to make sure you know what's going on there. The integral from 0 to 2 pi d theta, what does that integral give? There's no theta in here, so what happens? Just multiply this answer by 2 pi. So multiply by 2 pi and we've done the theta part. So the important part here is x hat direction, k sigma x and the 2 pi. Integral 0 to r a over a squared plus x squared, raise this thing to the 3/2, and we're integrating dA there. Okay, so there's basically our answer. That's our answer right there. So let's punch it in now. Let's punch it in now. So we have, let's find Wolfram alpha, so we can just do it kind of quick here. So we're looking at the integral of a divided by a squared plus x squared. I don't want to confuse Wolfram alpha though. So I have to tell it what to integrate over. From a equals 0 to a equals capital R. Let's see if it can do this for us real quick so we have a concrete answer here. If it doesn't do it for us this way, okay, it says it's taking extra time. So I'm going to replace a with something like y and ask it to integrate over y. So that's a little trick you can do if you ever have a bunch of constants in your expression. You can replace them with something like a y or a z.
Professor, can you show us what you're typing?
Yeah, I'll try to show it here in a second. It's telling me its standard computation time is being exceeded. So let's just look at an integral table here. Let me just pull up an integral table. If you have a TI-89, it shouldn't be too difficult to get the answer. Yeah, so here it is right here. So let me go ahead and share this with you guys. So I'll stop this share. And I will share over here in the web browser. Now, let me try and zoom in on it here. This integral here, don't get confused. This integral here, x over a squared plus x squared, is exactly the same integral that we have, except the x and the a are flipped. So this integral over x is what we need, okay? Can everybody see that? Let me open up the chat. Will Simbo Lab work? I don't know. Anything that can do integrals for you should probably work. The good old days when Wolfram Alpha was completely free are over, apparently. But yeah, so this is exactly the integral that we need. So we can see that the answer here is going to be a natural log. It's going to be a natural log. And when we plug in the value for a, which would be 0. By the way, this if we replace x with a and a with x, this integral is identical, right? It's perfectly symmetric. And so this literally is our answer here. It's 1/2 the log of a squared plus x squared. And then all we need to do is put our constants out that we had in front. So let me go ahead and stop sharing, and I'll share back to the whiteboard now, and we'll actually finalize our answer here. Our answer for E at the point P is going to be in the x hat direction. All our constants, k, sigma, x, the 2 pi. Let's put 2 pi first. 2 pi, k, sigma, x. And then it's a factor of 1/2, and then the natural log of x squared plus a squared. And it does use absolute value bars here, but we don't need absolute value bars because a is a radius of something, which is always positive, and x here is always positive. Okay, so we don't need the absolute value bars. The 1/2 here will cancel with the 2. And finally, we have our answer. Pi, Coulomb's constant, sigma, x, natural log of x squared plus a squared. Okay.
May I ask,
Go ahead.
what about that 3/2 that was in the integral?
Oh, wait a minute. Did I not?
There's a 3/2.
Oh my God. That's,
Yeah.
oh my God. How did I not notice that? Yeah, you're absolutely right. That is the wrong integral, as a matter of fact. Is there one here with a 3/2 power? Let me look. 3/2 power. Sorry, so this is not the correct answer. This is not the correct answer. Well, in any case, guys, I've told you how to do the integration. Let's go ahead and move on. Let's not spend too much time on it. We know up to this point everything is correct here. The integral over a is it's a simple u substitution. It's a simple u substitution to figure this answer out. Just do the substitution, u equals a squared plus x squared. And then it's the integral of the integral of 1 over u to the 3/2. It's a really easy integral to do. So let's not spend too much time on it. Sean says, don't give Wolfram Alpha definite integrals of more complicated equations. It will often time out. Okay, let's try that real quick. Let me see if I can get it to work without the definite integral. So let's take this piece out. Let me see, and I'll switch the share over if it works. Okay, and it worked. So let's take a look at that real quick, because so we can definitely see what the answer is here. Sharing the screen. Here's the Wolfram input here. So the integral is a over a squared plus b squared to the 3/2 power. And we're integrating over a, and so here it gives for the answer the integral minus 1 over the square root of a squared plus b squared, which is what you would expect from doing a simple u substitution. So once you have this answer here, replace the b squared with an x squared, and then multiply this answer by all of your constants, and you should be good to go there on that. Okay, any questions about this kind of process of going through integrating? It's a little bit complicated, but you should know how to set these problems up at the very least. So I might not require you to go through a lengthy integral like this, but maybe the basic setup of kind of getting everything in there without doing the integral is certainly something you should be able to do. So any questions about that? Give me a thumbs up if we're ready to kind of move forward. We're about an hour in, a little bit over an hour into the review session. If we need to go more than 2 hours, it's fine for me. I think I can go a little bit over 2 hours because the material for this class is it takes a little bit longer to kind of go through it than it does for my my trig based mechanics class. So we can maybe spend like another half hour or something if we need to. Okay, so let's clean this up. After electric fields, let's take a little bit of a time to discuss conductors and insulators. What is an insulator? An insulator is something that's not a conductor. Okay, so conductors allow charge to move through and around. Through, and what I mean by around is kind of like on the surface. So move through, let's be precise, move through the volume or on the surface, easily. Okay. And later in the class, in a couple chapters, we'll determine what we mean very precisely by easily. And it has to do with what we did in the lab on Thursday. It's just that idea of resistance. And it's very difficult to define a resistance for an insulator because it really doesn't allow charge to move through it, hardly at all. So resistance values for insulators are like massive. Okay. And sometimes you can't even really define one because no charge moves through it. But in any case, this is the definition here of a conductor. And so an insulator, we like to say, is not a conductor, whatever that means. And the reason we say it this way is because there are many different kinds of insulators. You can have insulators which are not allowing charge to flow, but then when you apply a certain potential difference, which is big enough, if the potential difference between, let's say, the left and the right side of this insulator is big enough, then all of a sudden it starts to behave like a conductor. And so you might be thinking to yourself something along the lines of like silicon chips in computers, right? So you apply a certain voltage to them, they start to conduct electricity. So this is like the area of what we call semiconductors. So there's a whole set of materials between conductors and insulators that we'd call semiconductors. So insulators, when you start to talk about insulators, you start to talk more about, like it's, to define it, you say it's not a conductor. Another way you could say it is it does not allow charge to flow easily through or on its surface. Okay, but we already know that charge is allowed to flow, right? We've seen it in the lab. A PVC pipe is not a conductor, it's an insulator. But if we get some charge on its surface, then we can transfer that charge between, let's say, it and another rod, for example. Or if we take the nylon blue cloth, which is an insulator, and we rub it against the PVC pipe, which is an insulator, we can still allow some charge to jump from one to the other. So charge is allowed to move in insulators, but it's as far as moving through insulators, it's much more difficult. Okay, so that's our little detour on conductors and insulators. Oh, actually, there's one more thing that I should point out, and that is that the electric field inside a conductor is always zero. Okay, the electric field inside of a conductor is always zero. The reason for that is because the charge in a conductor will always distribute itself on the surface of the conductor in such a way to cancel out the component of the electric field which is perpendicular to the conductor at that patch of area. Okay, it's more easily understood why that's the case once we talk about Gauss's law, because for Gauss's law, we know that only the charge inside of a closed surface counts. And so if we have a conductor with charge on the outside, even if we have an insulator with charge on the outside and no charge distributed on the inside, as long as that charge is distributed evenly on a symmetrical surface, for example, if you have a sphere, for example, if the charge is evenly distributed on the surface of that sphere, then the electric field on the inside of that sphere will be zero, even if it's an insulator. However, it's not easy for that charge to be evenly distributed on the surface of an insulator. And so there's no rule that says the electric field inside of an insulator is always zero. For a conductor, the electric field on the inside is always zero because the conductor will always allow the charge to evenly distribute itself on the surface of the conductor. Okay. All right, so I see that there's a chat. How many questions will be on this test? Well, I haven't decided the answer to that question yet. So I will try to make the test be designed for an hour and a half. And so however many questions that ends up being, that's my answer to you. So maybe somewhere between like 15 to 17 questions, something like that. Something like that. But again, if it depends on the difficulty of the questions as well, right? So 15 questions is usually pretty good for like an hour and 15-minute test. For an hour and a half, maybe I can throw 2 more questions on there, something like that. So that's my answer for you. I haven't decided yet, but hopefully that gives you an idea. Like maybe 15 to 17, maybe 20 if there's a couple, if I decide to throw a couple like easy questions on there, or well, questions that I think should be easy for you guys to answer, then I'll put a little bit more. But yeah, so any other questions before we go to Gauss's law now? Gauss's law is where things start to become a little bit simpler, right? Because it makes we don't have to do such complicated integration really to figure out the electric fields, right? So Gauss's law. Gauss's law is built on this idea of what we call electric flux. And electric flux is an integral over a closed surface for Gauss's law. It could be an open surface, but remember, if we have an open surface, then we can't necessarily uniquely define the flux. We can define the flux up to a minus sign. We usually refer to the surface with the letter capital S. And so if we had electric field lines, let's say, which kind of, let's say, look like this, and they're kind of curvy like so, and then we put a surface here like this, and this surface is kind of spherical, but maybe not so spherical, kind of maybe like a potato-shaped surface. Then what we do is we look at these patches where the electric field intersects the surface, and we draw the normal vector for that patch, right? And we compare the electric field to the normal vector using the dot product, right? So E dot dA there. And we integrate over the whole surface, the whole region of the surface, right? And so when we do that, we get the net electric flux, the total electric flux through that surface, okay? Now, it's pretty clear from this picture to me, maybe it's not clear to you guys, that there must be some charge distribution inside of this sphere. Can anybody tell us why there has to be some some charge distribution inside of this sphere here. Can anybody explain that to us? Why there has to be some charge distribution inside, given this picture here, with these electric field lines and this surface? And so the electric flux here would be positive. It would be a positive number. It would not be zero. It would not be negative. Does anybody have an explanation? David says the electric field is pointing outward. Alberto says it is because it is radiating outward in all directions. Yes, that's exactly right. That is exactly right. Even though it doesn't look like a point charge, right, where it's perfectly spherically symmetric, we know that this electric field, it's all going outward, right? So it must be coming from something. There must be some source of the electric field there. And what we would say, since now we've dealt with this stuff a little bit more, what we would say is that the divergence of the electric field, the dot product of this del operator, d by dx, d by dy, and these are partial derivatives, remember, not total derivatives. The dot product of this thing with the electric field would not be zero. It would be greater than zero in this case. And that tells us that there is a positive source of charge here on the inside. So there's some positive charges in here on this distribution. If it was less than zero, let's use another color. If it was less than zero, then what that would mean is we'd have some negative charge in here. And our electric field lines would be coming in this way for a negative distribution there. Only if the divergence of the electric field equal to zero would it mean that there's no flux, okay? If the divergence of E equals zero, this means that there is no flux. So a little bit of an extra bit of information there that maybe will help you understand flux a little bit better. How can I look at this thing and eyeball whether the divergence is zero, bigger than zero, less than zero? Well, if I have a situation like this where I have some electric field lines coming in and they're, so they're kind of coming in like this and then also kind of leaving out like this, then there's a chance that the electric flux will be zero. Okay, so I have some coming in and I have some coming out. There's a chance it'll be zero. Okay, but if it's all going out or all going in, then you can bet it's positive for all out and it's negative for all in, guaranteed. You can always get the sign of the flux by thinking about the divergence of E. Those of you who maybe aren't familiar with the physical meaning of the divergence tells you how radial the electric field is. So it tells you that like if I have electric field lines which are all kind of coming out like this, then my divergence is kind of a maximum when it's all radial like this, outward. When they're all in, that's a minimum because it's maximum negative, right? And if you have a situation like this, what's a good color? Yellow? Yellow you guys probably can't even see. If it's all kind of constant and like this, well, right, when we have something that's constant, you take derivatives of it, you get zero, right? So whenever you have a uniform electric field like this and you have a closed surface, it's always zero. You have it coming in and the same coming out, okay? So that's a little primer there for the electric flux. Now, what is Gauss's law? Gauss's law says, let's get off yellow. Gauss's law says that the electric flux is always equal to the charge enclosed, the charge inside divided by epsilon naught. Now there's a more complicated version of this in your book where it says, okay, we got to do a triple integral of the density of charge, you know, over some r prime over the volume here, and so forth, divided by epsilon naught. We know how to calculate the charge inside. We know how to do it. We know we have to integrate a charge density. This is the Gauss's law that we want to remember, that makes it so we're thinking logically here. We're not thinking about, oh, how does that integral go again, right? So just forget this. Don't remember this. Just think, how do I figure out the charge inside? Okay, well, if I have like a constant charge distribution, okay, I have like a rho dv, I can pull the rho out, and okay, what's the volume element? Okay, well, for a cylinder, it's going to be something like r d theta, r d theta dr, and then there's going to be like some sort of dz that I have to integrate over. Just try to think logically about it. Don't try to remember some complicated integral expression. Just figure out what the volume of the thing is going to be, and that tells you what the volume element is going to be, right? And then integrate over your charge distribution. Most charge distributions in this class are fairly simple, right? They're either constant or they're written down in a nice equation form where it doesn't depend on theta or it doesn't depend on x. It depends like just on r, for example, right? So we don't really want to mess with this we don't want to remember that. It's too complicated. We want to remember something simple like this. And even further than this is to remember this, right? Even further than that, we can take this to here. And this is a really nice equation to have memorized. Okay. So that's Gauss's law right there. So shall we look at the example of a uniformly charged insulating sphere and get the electric field on the inside of the sphere now? Give me a thumbs up if you want to see that example. Okay, Alberto says yes.
Yes, please.
Yes, okay, yes, lots of yeses. All right, let's take a look at that example now. So let's clean this up now. We have a sphere. It's an insulating sphere, so we have a rho, not a sigma. Sigma would be charges on the outside. Rho is charge everywhere on the inside. Okay, so let's suppose it's constant for simplicity. Okay, and it also means we can go through the example a little bit quicker. We need to draw a Gaussian surface, or in other words, some closed surface here. So let's draw a closed surface here with a radius r. The radius of our big sphere, we'll say, is capital R. And so when we draw this surface here, how much charge is enclosed inside of that surface? That's going to be given by the volume inside this surface times the charge density, which is constant. Okay, so the amount of charge inside is going to be equal to the charge density, which is constant, times the volume of our sphere there with little radius r. So it's going to be 4/3 pi r cubed. Okay. We could set this up as an integral, but why would we want to do integration when we can just do it simple? We have that the rho is constant here, so it's rho times the volume. The volume of charge that's inside this surface here is rho times 4/3 pi r cubed. All right, that's not Gauss's law though. What's the Gauss's law part? It says that the electric flux through that surface, that sphere of radius little r, we do E dot dA, integral over that closed surface, is equal to Q in over epsilon naught. Okay. Here, our dot product, let's review. How do we deal with this dot product here, right? What do we need to do? Well, we need to ask ourselves, okay, if the electric field here in this region is anything, if it's not zero, it has to be radially outward or radially inward. Why? Because we have spherical symmetry in this problem. So it has to be radially outward, it has to be radially inward, or it has to be zero. Those are the only options. It can't be pointing to the side because we have a uniform charge density on a sphere, we have radial symmetry. Okay, so it's either out or in. Let's suppose that rho is constant. Rho doesn't have, or sorry, let's suppose rho is positive. It doesn't have to be positive, it could be negative. If it's negative, we just make the answer negative in the end. Okay, we just replace rho with negative rho if we want the answer for negative charge. So it's as simple as that. All right, so if we do that, this is the electric field now. We know that the normal vector for any sphere is radially outward. Why is it radially outward? Because we established a convention that for a closed surface, the normal vector always points from the inside to the outside, and that defines the normal vector uniquely. In this case, n hat for a sphere is just the same direction as r hat, okay? So when we do this dot product here, dA is given by this patch, and the value, the vector dA, we should say, the vector dA is given as having a direction of r hat, or n hat, but n hat equals r hat here in this problem, times magnitude, and the magnitude is the dA part, the differential part. The r hat gives the direction, the dA gives the magnitude. Okay. So when we do E dot dA, well, E, we know E as a vector has to be magnitude of E times r hat. We just discussed it has to be in the radial direction. When we do the dot product now, E dot dA, we simply get E times dA, right? Dot product of two vectors is a scalar, so E dot dA gives E times dA when they're in the same direction. So now we need to integrate over this closed surface, E dA. Again, because of the radial symmetry, we can pull E out of the integral. Only because we have spherical symmetry can we do this. If we didn't have spherical symmetry, we couldn't do this. So E integral, closed integral of dA. Well, a closed integral means integrate over the whole sphere. What's the area of a sphere, guys? What's the area of a sphere? Surface area. You have to have this one memorized.
4 pi r squared.
4 pi r squared. See, it's easy, right? 4 pi r squared. You can, I think I told you guys this before, the volume is 4/3 pi r squared, and pi r cubed. A lot of people have the volume of a sphere memorized, but not the surface area. Take the derivative of the volume. Take the derivative with respect to r. If you take the derivative with respect to r, you get the surface area. There's a very good reason for that. When you take the derivative of something, it means you're looking at the boundary of that thing. When you're dealing with volumes and surfaces and things. What's the boundary of a sphere, like a ball? What's the boundary of a ball? It's that shell, the surface of the ball, the sphere we call it. Actually, when ball is actually the technical mathematical language for this volume here. We would call it a ball. Sphere is the mathematical language for just the outer shell with no inside. So you take the derivative of the ball, you get the sphere. Okay. So take the derivative of this volume expression. Most people have this one memorized, but they don't have this one memorized. Take the derivative. And the 3 comes down, cancels, and you're left with r squared. All right, enough about that. So it's 4 pi r squared there. 4 pi r squared. So E times 4 pi r squared. And this has to be equal to, this expression over here. Okay, so E 4 pi r squared is equal to rho 4/3 pi r squared, or cubed, sorry. I keep saying pi r cubed, but it's, 4/3 pi r squared, but it's 4/3 pi r cubed for the volume. Okay, 4/3 pi r cubed. All right, cancel what we can. We can cancel 4 pi and an r squared, 4 pi, and cancel this to a single power of r. What does that leave us with? It tells us that E is equal to rho. Oh, sorry, I forgot divided by epsilon naught. Divide this thing by epsilon naught. This is the charge, right? This is the charge, but it's not the charge divided by epsilon naught. So got to make sure we divide by epsilon naught. So rho over epsilon naught, there's a 3 here dividing, so put the 3, so rho over 3 epsilon naught. And then we just have linear dependence on R. Linear dependence on R inside of a uniformly charged insulating sphere. Can you commit that phrase to memory? Linear dependence on R for a uniformly charged insulating sphere. You don't have to remember it, because look at how easy it was to come up with that expression, right? If you want the full electric field with a vector, you just add the vector r hat. So if you want the full-blown vector, you put E with a vector over it, rho r over 3 epsilon naught, and then you put r hat. There you go. Now it's a vector. So what's the electric field doing here inside of this sphere? It's getting bigger and bigger as we go further and further away. Okay. I'm going to go ahead and clear this, but I'll rewrite what I just wrote, just so we have some more space here. So E is rho r over 3 epsilon naught, and then we put the r hat there. If you want the magnitude, it's just that first piece. The magnitude of E is just the first piece, rho r over 3 epsilon naught. The direction is r hat. Okay, so what's going on here? Well, if we're really close to the middle of the sphere, well, our electric field is small because r is small. So r is small, so the electric field is small. Okay, so there it is. Even though my mouse sucks, there it is. There's the electric field. Okay, but now as we get further and further away from the center, r is getting bigger, right? R is getting bigger. So now what's going on? Well, now we have more charge in here, so it makes sense. More charge means more electric field. So our electric field lines are getting bigger. They're getting bigger, right? There it is. Now when we get finally to the full size of the sphere, we have maximum electric field. Okay, I didn't mean to make that one curvy. So now we know the electric field there. And what's the value of the electric field here at the full radial distance? If this is big R, remember big R was the full size of the sphere. Well, we take this thing here and we plug in big R, and that's our answer. So E here has to be equal to rho big R over 3 epsilon naught. Okay, rho big R over 3 epsilon naught. That is the electric field at that location here, here, here. Anywhere on this sphere here, that's the value. Okay, but what's the value outside? What's the value here? Is it bigger? Is it smaller? Well, of course it's smaller, right? As we get further and further away from the charge, we will have less and less of an electric field. How much less? Well, we have to go through and use Gauss's law again, but we already know we can treat a sphere as a point charge when we're on the outside of the sphere. This is something that Isaac Newton knew a long time before Gauss, but Gauss was the one who showed mathematically using these integrals that was true. Newton already knew it was true and used it to do so much in physics already. He just didn't quite have the integration power that Gauss had. Okay, so what is the electric field here? Well, we treat this guy like a point charge. So it's KQ over R squared. And now what is R? Well, R is the distance. R is the distance from here to here, right? Same as before. The distance from the center to the point of interest. Okay? But what about Q? What is Q now? There's no charge. There's no charge here, right? Okay, so Q is just the total charge of the sphere. So the total charge of the sphere is equal to rho times the volume of the sphere. Well, the volume of the sphere is 4/3 pi big R cubed. Big R cubed. Okay, not little r cubed. That would be the volume of this sphere here. Okay, we don't want that volume. We just want the volume here. We just want the full volume of this sphere here. Okay, just that sphere. So it's big R cubed. So you plop that in there. So for your final answer, you'd have E equals, and you can do this with Gauss's law, by the way. Do a surface like this that's outside of the sphere, and you're going to get the same answer that you have here. So what do we have then? We have rho. There's a 4 here. There's a 3 in the bottom. And Coulomb's constant here is a 1 over 4 pi epsilon naught. So we can replace that. Let's put the Coulomb's constant in here. Rho, there's a pi, there's an r cubed, and then there's an r squared in the denominator. Okay, we can replace this Coulomb's constant with 1 over 4 pi epsilon naught, and then we can compare our answers. So rho over epsilon naught, we have a 3 in the denominator. We have a big R cubed up top, and we have an R squared in the bottom. And if we want to make this a vector, we put R hat. Now we can compare. Now we can compare these two. They have virtually the same form, right? So it's always important to do stuff like this with your answers. We have rho R over 3 epsilon naught. And we want to compare this. I want to compare this to rho R cubed over 3 epsilon naught R squared. You can see the units are the same, right? We have this guy up here. We have 3 powers of this guy, but 2 powers dividing. So the units are the same. If I plug in R equals big R, do I get the same answer? Do I get the same answer on the left as I get on the right? The answer is yes. If I plug in little r, I have rho big R over 3 epsilon naught for both of these answers. Perfect. That means the electric field is continuous. If we were to plot it, which is another thing that you should be able to do, we go like this. I plot it. It's linear up until big R. It's linear. And then what is it? It falls off as 1 over r squared towards infinity. This is E. Well, the magnitude of E. And this here, this is our little r axis. Okay. So any questions about that example there? Any questions about that example there?
Can you go over like a little bit how you got the electric field of the point that's outside of this sphere?
Okay, so you're talking about this. Let me.
Yes, that
you're
one.
talking about this one right here, right?
Yeah, that one.
Okay. So the logic here is coming all the way back from your first semester of physics. When you say that g, the gravitational acceleration, is constant. Why can we say that the gravitational field is constant when you're at the surface of the Earth? Well, the reason is because the Earth is so big that if you just climb a tall ladder or go to the top of a building, the height from the bottom of the building to the top of the building doesn't change much compared to the radius of the Earth, right? And so I'm going to delete this and I'll put this in more detail so you can really see what I'm talking about here. The gravitational force is big G, big M, which is the mass of the Earth, mass of some little person here or some object on Earth, which is nowhere near as big as Earth, right? Divided by the radius squared. If we're at the surface of the Earth, this is just the radius of Earth, right? Okay, but what if we're a distance h above? If we're a distance h above the surface of the Earth, we can write this r as big R, radius of the Earth, plus some height h, which is small compared to the radius of the Earth. Okay? And when we do that, what we see, let's write it out in steps here. My mouse is kind of giving me trouble again. When we do that, what we see is that we can factor out a radius of the Earth here. So in other words, divide h by the radius of the Earth. You factor it out. We have is g m e over m, and here we have radius of the Earth squared times 1 plus h over the radius of the Earth quantity squared. Does that make sense right there? Give me a thumbs up.
Yes.
Okay. If the radius of the Earth is 6.4 times 10 to the 6, sorry about the mouse, meters, 6.4 million meters, and h is 100 meters, what is this number approximately? We're dividing 100 by 6 million. It's approximately 0, right? It's negligible is the mathematical language. It's a negligible quantity. It doesn't matter. 1 plus something which is on the order of 10 to the negative 4 is virtually 1, right? When we go and we do our significant figures on our answer, the part of the answer which gives us, some resolution up to this decimal place is not gonna matter. 1 plus 0.00001 is still roughly 1. And so what we do is we discard this term and we're left with big G, mass of the Earth, the mass of the object you're interested in, divided by the radius of the Earth squared. And so it doesn't matter that you're above the surface, you get the same answer here. Now, if you set that equal to the force of gravity, well, then that means it's equal to the mass of the object you're looking at times its acceleration, and we call that acceleration g. We cancel both m's on each side, and by this analysis here that this h is small compared to the radius of the Earth, which of course is an analysis you've seen already in your Calculus 2 class. It's called Taylor expansion or Taylor series. If you write out the Taylor series for this thing, basically the same exact thing happens. You discard this h over r e term because it's too small compared to the other terms. Your Taylor series is going to depend on h over r sub e squared and h over r sub e cubed and h over r sub e to the fourth. And since it's of order 10 to the minus 4, as you square it, as you cube it, as you fourth it, it gets smaller and smaller and smaller and smaller, and in fact it gets exponentially smaller. Okay, so g is constant and is equal to this value. How is this relevant to E and M? It's exactly relevant to E and M. Why? Because this is essentially like looking at the Earth as if it were flat. Because you're on the surface of the Earth, you see the Earth as kind of looking flat if you look out in the distance. And when you do that, you get this constant g. And what it tells you is that all of the mass under your feet is what determines what g is. All of the mass beneath you is what determines g. And Isaac Newton figured this out by making this argument here. Okay? Gauss comes along and says, haha, I have these integrals that show me using Gauss's law that only the mass in the surface counts for the calculation of the field outside. G is like the electric field. G is the field. It's the vector field. E and G are vector fields, right? We have the electric field is the electric force over the charge. We have the acceleration gravitational field is the gravitational force over the gravitational charge, which is m, mass. These two things are basically identical objects, and so from a mathematical standpoint. And so when I go to calculate the electric field somewhere outside of the sphere, I just need to know the charge of the sphere, the total charge of the sphere. Okay? I just need to know the total charge of the sphere, and I can treat the sphere like a point. It's whatever is beneath me, so to speak. When I'm a person on the surface of Earth, I treat the Earth like a point charge when I plug in the radius of the Earth here and I calculate this G field. I'm treating the Earth like it's either flat or it's like a point charge, or like a point mass. Okay, because what do we do when we calculate the orbital velocity of a satellite? What do we do? Well, we say, here's our satellite over here. This is our satellite. And here's the Earth over here. And we're saying the gravitational force on this thing goes like, okay, this is terrible, my mouse, sorry. The gravitational field on this thing, oh my goodness. There we go, okay. The gravitational field on this thing, sorry, gravitational force, is equal to G, mass of the Earth, mass of the satellite divided by r squared. And r squared is the distance from the center of the Earth to the satellite. Well, now you should be saying, okay, if it's the distance from the satellite to the center of Earth, then we're treating the Earth as if it's a point charge, but it's a point mass, not a point charge. It's a point mass, because we've used this formula here. We can't use this formula for something that doesn't have spherical symmetry, right? And so Isaac Newton knew that we could treat the Earth as a point charge due to the symmetry of the problem. The fact that the Earth can be seen as flat close to the surface tells him that this thing is a sphere, but when I'm close to the surface of a sphere, I can treat it like it's flat, provided the distance I am above the surface is very small compared to the radius of the Earth, right? And then if we go out further, if the distance above the surface becomes relevant, becomes comparable to the size of the Earth, or even bigger to the size of the Earth. For example, when Isaac Newton thought about the moon, right, the apple falling on his head, he thought, okay, maybe the moon is also falling. When he goes through and he plugs in this force law to calculate the orbit of the moon, he's treating the Earth as if it were a point mass with all of the mass, all of this capital M here, concentrated at the center of the Earth. Okay, so that is really the physics of what's going on. We're treating this thing as if it's a point mass. All right, so what do we do in the case of electric fields? Well, we look at the sphere and it has this charge density rho. Well, the Earth also has a mass density rho, right? And we said, well, we'll look at a small volume of charge and we'll integrate over this thing. And it's going to give us a force at this point when we integrate over the entire volume here. And it's going to give us an electric force. And we'll divide that force by the total mass, or sorry, the mass of this thing here. And we'll get a gravitational force. And that gravitational force is the point. It's G-M-M over R squared. For Coulomb's law, we're saying this only works for a point. We say it's K Q1 over Q2 over R squared, and it only works for a point. Okay, but it doesn't only work for a point. It works for a spherical density of charge as long as we're outside the sphere. As long as we're outside the sphere, it works as if all of the charge is concentrated in this point here. Okay, what about the analogy of the flat Earth? Okay, if I look close to the surface of the sphere, if I draw a little tangent plane here close to the surface, okay, and I'm a person here, and I have some charge, so I'm going to experience an electrical charge. It's the exact same analysis. You plug in, okay, the radius of the R value that I'm interested in is the radius of the charged sphere plus a small amount, a small bit, h. And h is very small compared to capital R. And so what happens is you get for your answer rho times big R over 3 epsilon naught for the electric field magnitude. This is literally the identical calculation for G. The magnitude of G being equal to G big M over the radius of the Earth squared. It's exactly identical. It's exactly identical here. It's exactly identical. So does that answer your question? That was like a long-winded question. We can go past 6. It's not a big deal if we go past 6. But does that answer your question?
Yes.
Okay. hopefully that shed some light a little bit on more on the analogies that you have between gravity and electricity, because it's actually really nice, especially when you're thinking about like the gravitational potential energy versus electrical potential energy, right? Or gravitational potential, which is something you didn't talk about in your first semester, and electric potential, which is something we are talking about. Okay, so you always want to draw those analogies. That's Gauss's law. Any questions? Any questions? Let me ask you a question if there's no questions. Give me a thumbs up if I'm good to move forward. Give me a thumbs up if I'm good to move forward. 5, 6, 7, 8. Need a couple more. Thumbs up if you're ready to move forward. Juan, Carolyn, Caroline. Is it Caroline or Carolyn?
It's Carolyn.
Carolyn, okay. Charlotte, I didn't see you. Phoebe, I didn't see yours. Thumbs up if you're good. Yeah, it'll be posted. Okay, good. All right. So let me ask you guys a question now. Okay. Suppose I have a sheet of charge. Now, this is a sheet of charge with some thickness. Okay, this is a sheet of charge with some thickness. And this thing has a uniform charge density rho. So we have coordinate axes like this and like this. And we're interested in the electric field, let's say at some point over here or some point over here. Okay. We're interested in this electric field here. Question for you guys. It's a simple question. I'm not gonna ask you anything complicated. What kind of surface should you draw to figure out this electric field here? What kind of surface should you draw?
Is it a cylinder?
Is it a cylinder? You could indeed draw a cylinder. Are there any other surfaces you could draw? This is an infinite sheet of charge. So this sheet comes out of the board. It comes out of the board, it goes into the board, and it also goes infinitely up and down. Sphere or a circle? Box. I like box. I dislike sphere or a circle. The reason you don't want to draw a sphere is because if you draw a sphere, where's your symmetry gone? You've completely killed your symmetry, right? Because the electric field here at this point and at these 2 points might be different than your electric field over here at this point when you're further away from that slab. Okay. As a matter of fact, probably what you meant, maybe, I don't know for sure, is you meant a sphere here, because that's probably what you should draw if you were to draw a sphere. And you can get the correct answer with a sphere. The problem is you can't really say that the electric field is constant along the sphere without already knowing the answer, right? And so that makes doing this problem way harder if you're trying to derive the answer, right? So if you assume you already know the answer, right, there's no sense in doing the problem. So a box or a cylinder is best here. A box or a cylinder is best. I see some chat, so give me a second. In theory, we can use any shape, correct? It is just not feasible to use other shapes like a sphere. No, technically not true. You can use any shape if you're interested in the average electric field. If you're interested in the average electric field, use any shape. If you're interested in the electric field, you have to have some sort of symmetry, and you have to exploit that symmetry. Okay. Plane or no? Yeah, I like that. I like that logic there of using a plane because it extends infinitely in all directions. You don't have to do that, but yes, that's something that you can do. For example, you can draw a sphere in the following way. or sorry, a plane, excuse me. You can draw a plane. So did somebody say something?
Because this is the bus they were riding on 39 years ago.
I can't hear you.
Gunpoint and buried alive. It's a pain.
Somebody has some sound playing, like a video or something. Could you please turn that down so we can't hear that, or mute yourself? So Tatiana, what was your question again? So plane, and then did you ask me something, or?
No, I was just asking if we can use plane symmetry, maybe.
It does have planar symmetry, but you can't just use a plane. So I was going to show you what you have to do. So you have to think about, you put this plane here, but the plane isn't actually a plane, it's actually a box. So you have kind of an infinite box like this. Trying to draw a box here, but so you imagine you have a box, and it's an infinitely large box which captures the whole thing here. But what happens is that the area of this side doesn't matter. You just plug it in as A in Gauss's law. The areas of these two sides are just A, even though they're infinite, and you cancel them on both sides, because the amount of charge here inside this region here is going to have an A term on it as well. And so you cancel A's on both sides, and you're left with just the answer for the electric field. If you wanted to get the electric field on the inside of this thing, it's exactly the same. Choose the same shape, just shrink your shape symmetrically so that it's inside this charge distribution. Okay, so that was my question for you guys. Maybe let's do one more question for you guys. Let's make it a more complicated question now. Let's make it more complicated. So suppose I have a solid wire. No, actually, no, yeah, that's fine. So we have a solid wire here. So it's infinitely out of the screen and infinitely into the screen. Then we have a region here. Again, this is perfect. This is perfectly wraps around the wire. So these are cylinders. These are infinitely long cylinders. And this cylinder now has another charge density. Okay, hold on, not to my question yet. And then finally, we have this. Let's do this. And this one is hollow. This one is hollow. So it's a hollow cylinder here. It's empty. So no charge here in this region. No, maybe instead of saying hollow, I could just say, okay, actually what we'll say is let's say there's a charge density sigma on the surface, but there's no charge density inside this blue region. And we have a rho for the red region. And we have we have a rho 2. We have a rho 2 here, and we have a rho 1 here. Okay, so I have a rho 1, a rho 2, and a sigma. Okay, and this is supposed to be perfectly symmetric. So we have cylinders here. So what kind of symmetry do we have if we have cylinders? What kind of symmetry do we have if we have cylinders? Come on, this is an easy one. So somebody give the answer. Come on, this is an easy one. If we have cylinders, what kind of symmetry do we have? Is it spherical symmetry? Lambda. Not sure what you mean.
Cylindrical symmetry.
Thank you, Enzo. We have cylindrical symmetry when we have cylinders here. Okay, that means that we want to choose a cylinder for our surface, right? For our closed surface. Okay, so if we were going after the electric field here, let's think about the steps that we would take. We have several regions here. We have an inner region, 1, we have the second region, 2, we have this region, 3, and we have a region 4, right? We have 4 different regions we might want to know the electric field. Okay, So if we were going to use Gauss's law to get the electric field here, what would be the approach? What would be the approach? Okay. So think about that. Think about that answer. And I'll give you guys like a minute to think about that. Actually, maybe what we could do is we could break into the break rooms. We could go into the break rooms and I'll give everybody 2 minutes. I'll give you all 2 minutes and we'll make it so that we have we'll have 2 participants per room. Okay. We'll have 2 participants per room. Discuss what your approach would be to finding the electric field here. Okay, I'm going to open up the rooms. Go ahead and join your rooms. I'll give you guys 2 minutes. So in 1 minute, I'll give the warning that there's only 1 minute left. I am going to go around and join the rooms, but I won't say anything. I just want to hear some discussion. Go ahead and join your rooms, guys. Sean, I will put you in room 1. Sean, Duke, Juan, can you guys join your rooms? Duke, you there? Sean, you there? Juan, are you there? Okay, let's move people then.
Task.
Hello, Professor.
So anyway, yeah.
What if we use lambda to calculate the third one?
The third one, is there no electric field inside a hollow?
Oh yeah, no.
Oh wait, no.
Oh, hello, Professor.
Hello, Professor.
I know you say you weren't going to talk, but we were a little confused on what we're supposed to be discussing, like finding here.
You're discussing the general process to find the electric field. So kind of how you would set up the problem, what you would do to get to that answer.
Okay, I see.
If it helps you write some stuff down, right? But
yeah, we're on the right track-ish here then.
Okay, good. I'm gonna go to the next room.
All right.
Okay, thank you.
Thank you.
Is it the same? It's
yeah,
the EDA, right? The integral?
Oh, I mean,
why did it say recording? Oh.
So you're supposed to be discussing what to do to get the electric field, right? So continue the discussion and just let me listen for a second.
Oh. So, well, here's the thing. Professor, I'll be honest. The study session was it was a lot to cram for me, so I was kind of zoning out when you posed the question. So all I know is just from what I've seen, there's more than probably a few cylinders, no spheres, right? And it's easy to confuse the two due to the cross sections, but cylinders and we're finding the field, but I don't know like if it's insulated or we're finding it outside or inside, you know.
So we have 3 cylinders,
Uh-huh.
and those cylinders are concentric. There's no spheres or anything in the problem.
Okay.
You're just trying to figure out what you would do to find the electric field in all of those regions. So, for example, you could discuss what would we do to get the electric field in region 1? What could we do to get the electric field in the other regions, right?
Okay. And this is for an infinite sheet of charge, right?
There's
What
no
was-
infinite sheet.
Oh.
There are cylinders, right?
Oh, they're cylinders. The charges are cylinders.
No, the cylinders have uniform charge densities in 2 cases and a uniform surface charge in 1 case.
Oh, I mean, this is kind of a lot for me to visualize. Okay, but all right, that's fine. I think that's enough for us to have a discussion.
Carolyn, are you okay?
Like I forgot what the question was too.
So you just have some concentric cylinders and they have charges on their volumes, right? So what would you do to get the electric field given you have some objects which are charged and you're looking to find their electric field in different regions? So obviously we want to use Gauss's law, right? So the discussion should include Gauss's law.
Mm-hmm.
We have cylindrical symmetry. So the surfaces we're going to choose are going to be cylinders, for example.
Mm-hmm.
Okay. Does that help?
Yeah, a little significantly.
Okay. Draw your own picture and write some stuff down if you need to, right? To make it a little bit easier to visualize and so forth.
Yeah.
I'm going to go ahead and go to the next group now, okay?
Okay.
Mm-hmm.
Right.
Do you know how to draw on Zoom?
I don't hear any discussion in this room. Are you guys stuck?
Yeah.
What seems to be the confusion? Do we understand the question I'm asking? How to find the electric field in the 4 regions?
I actually had trouble understanding the question.
The question is, how would you go about finding the electric field in the 4 regions, given those concentric cylinders? Does that help, or should I? Where exactly is the confusion? Where exactly is the confusion? So I can explain a little bit better.
So I'm confused about what should I be explaining?
You should be trying to explain how you would calculate the electric field. What would you write down? What process are you going to use? We're obviously we're talking about Gauss's law, right? So we're obviously going to use Gauss's law, but we know it's not that simple, right? What kind of surface? You need a closed surface to write down Gauss's law, right? So what kind of closed surface are you going to write down for, your different regions here, and what is going to factor into your final answer for those electric fields in the different regions?
So we said a sphere or a circle is not a really good option, yeah?
Right, because we have cylindrical symmetry, right? So if we used a sphere, then that wouldn't be good. because that wouldn't be cylindrical symmetry. Does it make sense?
Yes. So how about a box then?
We have, so maybe, yeah. So you can use a box or you could use a sphere for Gauss's law, right? But when you see a Gauss's law problem, the first thing that you're asking is, what is the shape of the charge in? So what's the shape of the charge in this case? The charge distribution. They're cylinders, right?
Yeah.
Right.
So why would you want to choose a sphere or a box, right? That would break your symmetry.
That makes sense.
So what shape would you want to choose? One that has the same symmetry, which would be a
cylinder.
Right. And so just to give a little bit more, because it seems like we're stuck on starting here. So just to give a little bit more, we have 4 regions of interest, right? So in those 4 regions, we would want to draw 4 different cylinders, right? And then once you draw those cylinders, then you ask yourself, okay, so what is the electric field going to look like in this case? Like if I write down Gauss's law in this region, what does it look like? If I write down Gauss's law in the second region, what does that look like? Is there anything special I need to account for? Same for the third and the fourth regions, right? So that's the idea. Juan, do you have any information or questions you want to? What'd you say? Okay. So yeah, it's open. It should be open discussion. So discuss, like, so David, seems like you're maybe a little bit ahead. So you and Kareem communicate. Juan, hopefully your mic sounds really poor quality, so I don't know, maybe you can't add to the discussion much, but yeah, try to have a little discussion. I'm going to go check on another group that I said I would come back to them. Okay.
All right. Thank you, Professor.
Yeah. We will talk about it when the rooms close and everything. So.
Are you?
Oh, hello, instructor. Yeah, so we kind of discussed some general strategies on how to solve the problem, we think, but we're pretty sure that we're wrong. So
just discuss your strategies so I can listen.
Well, I can tell. Okay, so I'll share mine, and because there's still parts of the question I don't understand, like if we're focusing with just surface area or we're also taking volume into consideration. But it's kind of like how we would tackle any.
Why couldn't it be both?
Oh, yeah, it could be both. So it could be one, it could be or the other, or it could be both.
So let me add to that. We have a charge density rho, right?
Okay. Oh, yeah. So I didn't know about that.
Yeah. So in order to find the charge, right, we would have to know the volume. And then for the side with the E dot dA, well, we always have to deal with air on that side, right?
Yeah. Yeah. So we would still find the surface area. How I really meant to phrase what I was saying is I didn't know if we were finding I didn't know about the charge density. So when I spoke about volumes or areas, that was with regards to charge density. Of course, when it comes to applying Gauss's law, we always take surface area into consideration. But for me, another thing I didn't understand, but I mean, assuming it encloses one cylinder, right? By it, I'm talking about the charge. I mean, what I would do is do E, I'm assuming a uniform field. We know the surface of a cylinder is 2 pi RL.
You said you would assume a uniform field.
Yeah, as in we can pull it out of the integration.
Right. So something like that is a perfect thing to discuss with your partner here, right? So when we set up Gauss's law for this region, it looks like because of the symmetry, we can pull the electric field out of the integral, right? And so forth. Continue the discussion, right?
Yeah, yeah.
I want to check in on another group that also
Oh,
they wanted me to come back because
okay,
so let me go do that, and pretty soon I'll close the rooms and we'll just discuss.
okay.
Carolyn, did you have any questions before I go?
Not really. Not at the moment I can think of. I'm just trying to visualize the electric field
Okay.
in the cylinder. Yeah, because I'm assuming that the cylinders in the electric field would be batteries, correct?
It would
Or
be what?
batteries,
What do you mean?
like because you were saying cylinders or something. Mm,
Uh-huh.
yeah, and
Oh,
so
you mean like the electric field of like a battery?
I think so. I believe
So
so.
so what you should think about for this problem is probably like a long wire, like an infinitely long wire, which has a little bit of thickness.
Oh,
There's obviously another cylinder around that wire, and then there's a third cylinder around that wire again, right?
okay.
Um, maybe that helps you visualize better.
Yeah.
Okay, so I'm going to go to the other group now. So continue the discussion.
All right. Yeah, so kind of like how I told the instructor. Now,
Okay, I noticed that some people left their room. So Enzo, Phoebe.
Yeah, we were just unsure because we're like, it's been a few minutes where we just supposed to leave on our own and we just
I'm
weren't
just
sure.
getting,
So that's why we did it.
I'm just getting questions, so I'm
Oh,
trying to
okay.
answer people's questions as they come.
Yeah, we just were unsure, that's all.
So what's the status for you two?
We came up with what we think might be how to set it up formula like on the formula, but we're not like very confident on it. I've not been good with cylindrical sheets like this. That was one of my weak points. So we're not like too confident about it, but we came up with an answer.
Okay. Do you have any questions? Either of you?
I don't.
Yeah, me neither.
Okay. All right. I'm gonna think there's maybe one more group I need to go back to.
Hello,
Hi.
Professor.
Oh, hi. Actually,
So when I join, I want to hear discussion.
oh yeah, we were talking about the cylinders at the beginning. I think the general consent. I think the route we will take was to add, add inner cylinders, the innermost and the other one, and the outside cylinder. I don't think it has an effect since there's no charge, but I might be wrong.
We have row.
Okay. That I think I hear some good stuff in there. Yeah. So I'm gonna close the groups here. I'm gonna actually give the 1 minute warning or whatever now for people to leave their groups, and then we'll talk about it as a class.
Okay, thank you, Professor.
Is everybody back? Has everyone returned? Give me a thumbs up. Okay, good. Looks like, I think everyone. Okay, so we asked the following question. Suppose we have these 3 concentric cylinders. What would our strategy be for finding the electric field in all 4 of these regions here? So we have 1, we have 2, we have 3, and we have 4. We have 4 regions. What would the strategy be? Well, first and foremost, we have cylinders, right? We have 3 cylinders here. So we want to exploit the cylindrical symmetry and use Gauss's law. Okay. So let's go ahead and try to pick a color here that maybe we can all see. So I want to choose a cylinder here. If I want to know the electric field in this region 1 here, something like this, right? E dot dA for region 1 equals the Q inside divided by epsilon naught. What's the Q inside going to be? Well, the Q inside, we got to figure out what it is, right? We have these charge densities, rho 1. We have to integrate with respect to the volume, right? So the simplest case would be just rho is constant, right? If rho is constant, that's nice and easy. It pulls out of the integral and we just have to integrate dV, right? And for a cylinder, dV is something like r dr d theta, and then dz, for example, if the z-axis is coming in and out of the board. So if that's the case, then doing that integral there, if rho is constant, it's super simple, right? You pull rho out of the integral and you multiply by the volume of a cylinder. Something like this. So Q in, if this is constant, and then you just multiply by the volume of the cylinder. The volume of the cylinder is 2 pi, pi r squared, times the height of the cylinder, or in this case, I've used z here, so I could just times z. You might be worried, wait a minute, z, these cylinders are infinite cylinders, so z is basically infinity. Well, let's just deal with that later because it's going to cancel on both sides, right? So in reality, what we would do is we would just kind of not do this z integration, and we see that there's also a z integration on the left side, and so we kind of just discard that. Okay, so we've got the charge inside, but this is just for region 1 though. This is just for region 1. So for region 1, things kind of simplify. Since we have a cylinder, we know our electric field lines are going to be radially outward from the cylinder along the axis of the cylinder, right? The radial axis for the cylinder. So radially outward like this. It's also going to be uniform. The electric field will be uniform if it only depends on the radius. If it only depends on r, right? Kind of like for a sphere. The electric field is the same everywhere once you fix the radius. So as long as there's no angular dependence, E pulls out of the integral. What's dA for a cylinder in this case? Well, we don't care about the caps of the cylinder. We only care about the body of the cylinder. So kind of a more three-dimensional diagram. We have electric field lines coming out like this, like so, right? So we only care about the body. We don't care about the caps. There's no electric field perpendicular to these caps. So we don't worry about it. We just look at the body. All right, well, the body of the cylinder has an area of the circumference of the circle of the cap, 2 pi r, times the length. And the length here is what we said for z. So already we see the z's are going to cancel here on both sides, right? And cancellation of the z's, perfect, because that's where our infinity is. So those guys will cancel out. And there's some cancellation of some other stuff, right? Like the pi's will cancel on both sides and so forth. The point of this question, though, is how do we set it up? How do we set it up? So we're not going to go through the motions of doing everything here. What do we do for the second region? Draw our cylinder again, draw our surface, which is a cylinder. I haven't drawn a perfect cylinder here, but that's what it's supposed to be. It's supposed to be a perfect cylinder in region 2. Well, in region 2, that's where things, okay, now they start to get maybe a little bit more complicated. We have all of the charge from region 1 plus some charge in region 2. What that means is the charge inside this surface for region 2 is equal to the charge, the total charge in region 1 plus now an integral over rho 2 over the volume. But this time, the volume is going to be different. We don't integrate over the volume in this inner region anymore. We just integrate over this volume here, this region. Okay? That's how we get that charge right there from region 2. We just integrate in region 2. So for example, we would integrate R from R1 up to an R value which is less than R2. Okay, so suppose we have this radius here. This is like an R1. R1 here, my mouse kind of, here we go, R1. Okay, and then we have this region here, which is an R2. We have this region here, which is an R3. And the distance from the center to the edge of a surface, that's what we would leave little r for, right? So for this second piece in region 2, we would need to integrate from R1 up to some intermediate radius lowercase r. And lowercase r is what we typically use as the variable, right? Okay, same thing for region 3 now. If we put a sphere in region 3, okay, now we have in region 3 the total amount of charge inside that region is equal to the total amount of charge in region 1 plus the total amount of charge from region 2 plus, and then we integrate the charge density in this region right here. But the charge density in this region right here is 0 because we only have a surface charge. We only have a surface charge on the outside of the blue cylinder. And so it'd be plus 0 here. Okay. So that's for the charge inside. Again, the idea for the electric field is the same for all of the regions because we have radial symmetry. If we put region 2 now, if my mouse works, if we put region 2, we're going to pull out the electric field in region 2 because it's going to be radially symmetric again. And our dA here is going to be the same. It's going to be 2 pi r times z, right? And that's going to factor out the z. The z is going to cancel on both sides is what I'm saying. What about for region 3 for the electric field? If we do region 3 for the electric field, what happens? Well, there's no charge density in region 3, but definitely there's an electric field in region 3. Since there's no charge in region 3, we can treat the black portion. We can treat the black portion and the red portion here, we can treat this as the only charge in the problem. And so it's simply the total amount of charge Q1 and Q2, and there's no additional charge on the right side. And so our electric field again has to be radially symmetric. We pull it out, even in region 3, where there's no charge, because all that matters for Gauss's law is the charge inside divided by epsilon naught. And so as we get further away from the charge inside, from the red region, as we get further and further away, the electric field should decrease. So here the electric field is actually bigger than here. The electric field should decrease as we approach the surface of the blue cylinder. Okay? And then once we get real close to the surface of the blue cylinder, the electric field will be as small as it's going to be for that region. And then as soon as we cross into the region where we have sigma, the fourth region, then we have to figure out how much charge there is on that final cylinder. So for 4 here, for region 4, we have to find the total amount of charge in region 4. So it's going to be the total for 1 plus the total for 2 plus the total for the cylinder, or sorry, for the final cylinder there, which oh, we should write that out. We shouldn't. Let's not say the total there. How would we find the total? Well, we would integrate sigma dA. But if sigma is constant, it would just be the area of that cylinder times sigma. And again, this is going to have the whole thing with the 2 pi r times z. All of these terms have to have some sort of 2 pi r times z. So that z, which is infinity, cancels out on all of the sides of our equation, cancels out in all of the terms. So there's no infinity in our problem. Okay, so that's the general thought process there. You're applying Gauss's law in each of those regions. I'm pretty sure I gave you guys a homework problem that has concentric spheres. So review that problem from the homework if you're kind of confused by what's going on here. Maybe that problem will help you kind of understand what's going on here. Applying Gauss's law multiple times. The idea is for each region in your problem, you have to do Gauss's law. So if you have 4 regions, you've got to do Gauss's law 4 different times. And you've got to remember to account for all of the charge on the inside. So we have 2 different charge densities here in the middle. We have the rho 1 and the rho 2. So when we do our integration, for example, in the first region, it's just the integral of rho 1, right? We go from 0 to r. Well, in region 2, we have to integrate, we have to find the total charge in region 1, plus we have to integrate to find the charge just from the red cylinder. So we have to integrate from R1 up to R to get the total amount of charge there for the red cylinder. And then the black charge plus the red charge is Q inside, the total charge for region 2. For region 3, we're not adding any more charge anymore. When we're in region 3, it's just all of the black and all of the red charge. So add those together. And then when we get into region 4, then we have to add in the fact that there's a surface charge there on that last cylinder. So that's the thought process there. That's the thought process. Any questions about how to approach that problem there? We're not going to do the example specifically here. I'd have to kind of give you some more information and stuff, but any questions about that? You can write them in the chat or use the hand emoji, or you can just speak up. Give me a thumbs up if that's good. Okay, we need to see more than just half. David, Sergio, Joseph, Carolyn, Duke, Sean. Okay, much better. Okay, so that's the philosophy of it. That's how you approach those Gauss's law problems. More regions means more Gauss's law. That's basically what it is. Always exploit your symmetry. Always exploit your symmetry. So if a problem says you have cylinders, then that means that's your symmetry. Your symmetry is cylindrical symmetry. You're going to choose cylinders for your Gauss's law surfaces. Okay, cylinders in the problem means cylinder surfaces. Okay, that's the idea. If a problem says you have spheres, then you're going to choose a sphere. If a problem says you have a plane of charge or two planes of charge, or you have a thick slab of charge, then you're going to want to use some surface which has planar symmetry. That could be a cylinder or a box. Okay, cylinder or a box. Matter of fact, it could be any shape which has flat sides like a plane does. So like you could choose some sort of like pyramid style shape if you wanted to, but you don't have to. Okay. All right. Let's take a look at electric potential now, or electric chapter 23. We'll try to end things off before 7 o'clock so we can all enjoy dinner. And then I still have a surprise for you guys. So the surprise, let's just go ahead and take care of that now. The surprise is the following. I'm going to extend homework assignments from week 1 and week 2. Only just the pre-lectures and the homeworks. I will extend them until Sunday, 11:59 p.m. Okay, so just until Sunday. So it's not meant to be for the students who did the assignments already. If you've already done the assignments, then this is not for you. This is for the people who, kind of like me, had a really crazy first week. I see that there's a number of students who just kind of took zeros on the first couple assignments and then kind of did work on the second week assignments. That's kind of when they started. So I want to make sure that everybody can have some chance to catch up on points. And also, since that stuff was the first week, it's a good opportunity to review. So even if you've done the assignments, you can go back and try and score some extra points doing those ones that you weren't able to visit. Okay, so that's going to be, so it's extensions, week 1 and 2 to Sunday, 11:59 p.m. Okay. Extensions until Sunday, 11:59 p.m. So I know that that's not, not everybody is going to have time to do that, but for those of you who do, I'm just going to do that because we have a test coming up, right? And everything was kind of rocky in the first 2 weeks there. So there you go. All right. Electric potential. Whoops, I erased it. Okay, we just won't write it again. Electric potential. What is it? Well, first we kind of visited this idea of the work done on a charge is this integral of Q E on some path given by dr, and we said we did this on some curve. We called it C, or call it a path, some curve or path C. And this was an amount of electrical work. And if it was conservative, if the curl of E, if I can get my mouse to work here, the curl of E is 0. If the curl of E is 0, then that implied that it didn't depend on the path anymore. So the integral C1, oh my goodness. Oh my God. Okay, let's, come on. There we go. Maybe we'll just use text here. So C, the integral of, C1 I should have put. C1 is equal to the integral of that thing there, C2. Okay, there we go. It's working now. So the integral of E dot dr on a path C1 is the same as an integral on a path C2, provided that the endpoints. Okay, now my mouse is working. For C1 and C2 are the same. Now it's not. The same. Okay, so provided they're the same, then we have we have this this thing here. So if E is conservative, the integral on these two paths is the same, provided they have the same endpoints. And that is if and only if. So any vector field where the integral on two different paths with the same endpoints is the same, where the two paths are arbitrary, so it has to be on all paths actually, not just two paths, then that implies that the curl of that vector field is also 0. Okay, so that is if and only if. So the curves C1 and C2 are arbitrary, but they have the same endpoints. All right, when we do that, we can say this is equal to minus the change in potential energy, electric potential energy. Sometimes you see E in these books, sometimes no E. I don't think there is an E subscript in this book. We have a chat. I suggest you use a moist nude trough brush and Q-tip to clear up the mouse, the tooth. What do you mean? I'm not sure what
A toothbrush, like a wet toothbrush, slightly moist, and then rub it inside around the areas of the mouse with a mouse click.
Oh, I see. To clean the mouse. I got you. Yeah, actually, I've tried to clean it before, and nothing ever works actually. So yeah, maybe I should try and just get a new mouse. But yeah, okay. So once we have the potential energy defined, then what we did was we saw that we had to have two charges, a Q1 and a Q2, in order to have potential energy in our problem. Okay, Q1 and Q2, the potential energy is K Q1 Q2 over R squared, where R is the distance between those two charges. And if we had more than two charges, things start to get more complicated. There's more bookkeeping. So if I add a third charge now, this is a third charge here, Q3. Third charge Q3 here. Okay, if we add a third charge, now we have two charges that we have to account for when we add in the potential energy. So if this is R12, then this changes to R12 squared. Then we have R13, and we have R23 as well. And so we have to add in a Q2 Q3 over R23 squared. And of course, Coulomb's constant is still there. And we have a Coulomb's constant Q1 Q3 over R13. And it gets to the point where you can write down a double sum. It's possible to write down a double summation and calculate the potential energy for like an n charges. Okay, but that's that's kind of, it's not that useful. We just want to kind of remember, if we get two charges in here, we have a potential energy. One charge, no potential energy. Two charges, we have potential energy now. If we add in a third charge, then we have to add in two more terms. If we add in a fourth charge, then we have to add three more terms. If we add in a fifth charge, we have to add in four more terms, and so forth. So the number of terms increases as n increases, the number of charges. Okay. And another way of kind of understanding the potential energy here is you can also understand it in terms of something like you have a sphere of charge here. You have a sphere that's charged, and it has a total charge Q. And there's an electric field associated with that charge, right? Which, let's say at this location points in this direction. And the electric field is 0 at infinity, but we want to bring a positive charge here. Let's call it like Q. Let's just call it lowercase q. We want to bring this charge in from infinity to this location here. You can also calculate a potential energy for that as well. And the way you would do that is by using that integral expression. So you would calculate the integral of E dot dr on this straight line path here from this location B, which is at r equals infinity, or r tends to infinity there, and up to this point A, which is a distance of r away from the center of that sphere. And so you could account for situations where you have a charge distribution, like you have this sphere which has a charge distribution. In this case, if it just has a uniform charge distribution and it has a total charge Q, we can write down the electric field nice and easy. It's K big Q over R squared. And we can do this integral here. And the mistake that I made when I was going through the electric potential here was I said that we would measure dr in this direction. And I guess I was just kind of stuck in a Gauss's law mode where I thought I had this choice I could make. In reality, there's no choice here because r is big over here at point B and r is small over here at point A. What that means is that dr is actually measured in this direction. There's no choice there. So I was in Gauss's law mode, I guess. I just made that mistake. So dr as a vector, is equal to dr magnitude times r hat. There's no minus sign there. So hopefully you guys saw my email and saw that mistake there. So if you go back and you change it in your notes, it should read like this, no minus sign there. I double counted the minus sign because we were already integrating from big R to little r, and that already introduces a minus sign when you do an integral. So I overcounted that minus sign. So this is correct here. So dr equals dr times r hat. Okay. So yeah, we can also get an electric potential energy here in this case too. So if the electric field here is kq over r squared, kq over r squared, right? And we want to integrate this thing dr. We're going to integrate from infinity up to r sub a, let's say, if we want to call this r sub a. And that's how, and that's our answer. Oh, sorry, I forgot the little q. So the little q goes outside, right? So it's little q. This is the amount of work done, right? And so this is minus the change in potential energy. And when all is said and done, you're gonna get an answer which looks identical to 2-point charges. Again, it's this idea that when you have spherical symmetry, you have a sphere with charge density. As long as you're outside of that sphere, then you treat that sphere as a point with all of the charge concentrated at a point. And so what we're going to get for this answer here, just to finish it off, is K big Q, which is the charge of the sphere, the total charge, times that little q over r. And this is going to be your change in potential energy here, which essentially is just your potential energy for this charge configuration, because you bring in this little charge q from infinity up to the point A. Okay. And if you go through this, you will get the correct sign. You will get the correct sign if you go through that as is. Okay. So that's electric potential energy. What about electric potential? Well, what we do for electric potential is we say that the electric potential is the potential energy per unit charge. And it's that simple. And everything we've done up to this point is virtually the same, except we now say, we just kind of change the order of things. We put the minus sign on the other side with the integral, and we say it's an integral of E dot dr here. And this is over some curve C or some path. And again, E is conservative for electrostatics, right? Because we can write down all of our electric fields in terms of integrals of point charges, right? So we had the following statement. We said that if we were to close off this integral here, if we did a closed integral on a closed path C, or closed curve C, or closed contour C, you see all kinds of different language when they in math, of E dot dr, it would just be equal to 0. If we close this integral off, it would be equal to 0. And we said that this here led us to Kirchhoff's voltage law, which says that the sum of all the voltages around a closed loop was equal to 0. And then an obvious question to ask is, how does this imply this here, right? When I kind of gave you, a little bit more information here. I said there's going to be a law that we're going to look at in the future called Faraday's law. And what Faraday's law is it's an electric potential due to a magnetic field, a time-changing magnetic field. And so that's not electrostatics anymore, right? If we have a time-changing magnetic field, we're not doing electrostatics anymore. And as a matter of fact, the electric field will depend on time if we have a time-changing magnetic field. Electric and magnetic fields are connected in a way that we'll write down eventually. So I kind of said, well, this KVL, Kirchhoff's voltage law, is actually true in general. And the reason it's true in general has to do with the fact that these electric potential differences don't have to be due to an electric field. They can also be electric potential differences due to magnetic fields. And as long as we account for all of the electric potential differences, when we go around a closed loop and we sum them all up, we'll get 0. And the reason we'll get 0 is because this electric potential function, it really is a function. It only has one value at any point. So it's impossible to have multiple values at a single point. Okay. And so simply mathematically, this is just a true statement here. The sum of all of the potential differences around a closed loop is equal to 0. Okay. So maybe we can look at an example quickly before I leave you guys. So a nice example that we're going to use in the future, so that's why I will use it now. And actually, let me draw things really simply. We will have 2 parallel sheets, which are infinite. So these are two parallel sheets. Of uniform charge density. Okay. Each one having opposite charge of the other. Equal and opposite charge. So this one has plus Q and this one has minus Q. The electric field in here points from left to right, and it has a magnitude of sigma over epsilon naught. Why is it not sigma over 2 epsilon naught? Because we have 2 sheets. So it's twice as much electric field. Remember that idea of the principle of superposition? We add the electric fields as vectors. So the electric field in here is twice as big as it was before. And as a matter of fact, the electric field outside cancels out because we have minus charge on this plate and plus charge on this plate. So they're in the opposite direction. outside of the two sheets. So towards the negative for this one and away from the positive for this one. And so we get E is 0 on the outside. Okay, so principle of superposition there. So the electric field is sigma over epsilon naught here in the inside. So if we wanted to take a charge, a little q here, and allow it to go from the positive plate to the negative plate, a distance d, we call that the separation distance, the distance between the two plates. And that's coming up next chapter when we talk about capacitors. It turns out that for a nice constant electric field like this, a real nice and easy simple formula to remember is that the electric field times the distance d is equal to the change in the potential difference. So the change in potential difference, E times d, simple. Where does that come from? Well, it comes from that integral expression, E dot dr, but it turns out E is constant, and you're integrating over a straight line path from here to here. It's a straight line path. And so you just pick up the distance d, nice and easy. Now, normally we'd put a minus sign here, but we're just looking at magnitude here, the magnitude of the potential difference. We know that the potential is higher on the positive plate and is lower on the negative plate, okay? So what we typically write is plus and then delta V and then a minus like so. And that indicates which side is at a higher potential. The plus is at the higher potential, the minus is at the lower potential, okay? Is work being done on this charge? The electric field is doing work on the charge, right? The electric field is doing work on the charge. The electric field is exerting a force on this positive charge, and it's moving in the rightward direction, which is the same direction as the electric field. And so positive work is being done on the charge by the electric field. And so this charge has a negative change in potential energy or a negative change in voltage. Obviously, it goes from high to low. So the final is lower than the initial. And so it's a negative change. But oftentimes, just having the magnitude of the change is really good for solving problems, especially heading into the next chapter. All right, so do we have any questions? I can answer some questions for several minutes here if you guys want.
I was just gonna ask, how do you express the work done for this one? Would it be like W equals delta V over Q?
The work done is just the force times the change in potential. So it's QED. And this time the sign is already correct because we know that it's going from high potential to low potential. So delta V is negative. So therefore the work is positive. Does that make sense? So this is the same as setting it up as Q integral on some path E dot dr. And dr and E are parallel here. They're both pointing to the right. So when you do the dot product, you don't pick up a minus sign or anything like that. The electric field is constant. It pulls right out of the integral. What's the length of the path? Well, the length of the path is d because you're going from the plus to the minus plate. Does that clarify or?
Yeah, thank you, Professor.
Okay. Any other questions? Feel free to ask. You don't have to ask me questions about this either. If you want to ask me a question about Gauss's law, if you want to ask me a question about Coulomb's law, feel free. If not, I will end the session now. If you want to, you can kind of stick around if you want to ask me a private question or something like that, but feel free to leave the call. The session is officially over, and we will do an in-class session as well before the test. So hopefully we'll have plenty of review. We can do more examples on Tuesday.
This session will be recorded, posted on YouTube, right?
Yes.
Okay, thank you.
Alberto, David, Sean, Sergio, are you guys here?
Yeah.
Do you have questions? Go ahead and ask your questions. Who wants to go first?
Well, for me, it has to do with my Pearson thing. I'd rather ask last since it's possibly the least important and it's not related to the work we did.
Sean, do you have a question? Are you there, Sean? Okay, Sergio, just ask your question then, and then I'll end the call after I answer.
Yeah. So I was supposed to get my financial aid settled, I guess, by Friday, but I looked more into it and I guess it can take up to 48 hours. So I'm guessing worst case scenario, I'm hoping I get it tomorrow morning because I still need to pay for the Pearson. I don't know what it's called, my mastering something. What we use for homework. So I just wanted to let you know that because I still don't have access to it.
Okay.
Yeah. So hopefully tomorrow I'll message you in the morning. Then
Okay.
yeah. All right. I think that's it. Thank you.
All right. Thanks. I'm going to extend all the assignments now.
Okay.
So hopefully tomorrow morning,
Yeah,
we'll
I'm
have
really
access to
praying.
stuff, and I can extend the other ones for you too. But keep in mind that I'm also extending some of those older assignments too. So if you work on the ones you already need to do, and you have some extra time, you can.
Yeah, no, yeah, I'm gonna do it. Of course, I'm gonna take advantage of that time. Thank you as well for that.
Yeah, no problem.
All right.
All right, I'm going to end the meeting now. Okay. Have a good night.
All right. You too.